I received these digital Hall effect 6 to 36 volt proximity sensors. And for those of you who are following my channel, you will know that I've already done a video talking about this form factor of sensor. But I got a lot of great comments on that video, and in combination with receiving these new sensors, I thought the issue was worth revisiting. Now I can summarize the rest of this video and just give you the takeaway, and that is, just like I said in the last video, this form factor of 6 to 36 volt and to 10 to 30 volt sensor will absolutely work on 3D printers for auto leveling, auto mesh bed leveling. There's two qualifiers to that. The first is I recommend that you slice off the plastic off the bottom of these. That will give you a little bit more clearance off your bed, which is always good to have. And the other thing is, when you perform your auto mesh bed leveling algorithm, always do it on a fairly cold bed that's always the same temperature. So we'll get into the specifics of why you need to do it that way in the rest of the video. But before we do that, I want to give a big shout out and thanks to everyone who's subscribed. 6 videos in on this channel and I'm already at 1,000 subscribers. It's blowing me away. So this is fast becoming way more than a hobby, and that's just, it's making me really happy. So thank you very much for that. But even with 1,000 subscribers, if I monetize this channel, I'll make like $5 or $10 off this video. And I've spent probably 25 hours to make this video. So I'm asking you to go to my Patreon page, and I'll provide a link in the description below. And hey, toss me a couple of bucks, become a $5 a month continuing subscriber, and you're gonna get access to all of the 3D printable files that I'm making for 3 4-color printers that are coming up. There's gonna be a lot of extras above and beyond just the regular stuff you get here on YouTube that are available to the Patreon donation folks. So please do that. Okay, without further delay, let's continue with the rest of this video. What I'm going to do is very carefully slice right here in between the epoxy and the blue plastic. And the idea is to just cleave it right in between the two. The epoxy sticks to the plastic, but it's not a perfect adhesion. So get that going on there. And you want to use a utility knife because you see how thin the knife is, and it's able to split the plastic nicely. So you can see what's going on there. It's just going right on down. You might be able to get away with that with a normal kind of knife, but I find utility knives work really well for this type of thing. So yeah, there we go. And we can see the electromagnet and that gap there where the Hall effect sensor goes. And now that it's completely sliced off, we've saved ourselves the thickness of that plastic. We can trim it up a little at the back here. And then after I'm done with that, because I want to, if it does collide with the parts, like if I get any peeling of my part off on the first layer, I want to have it be able to kind of skip up over that part nicely. So put this little chamfer on the corner. It's a lot easier to put the chamfer on the plastic than it is on the epoxy. The epoxy is kind of brittle. So as big of a chamfer as you want, as long as you're only cutting plastic and not cutting too much epoxy. We don't really know because we can't see where the electronics are, so you want to make sure you don't cut into them. So there you have it. Nice trimmed and chamfered sensor, which gives you some extra clearance. We have here the usual suspects from the last video. This is the 10 to 30 volt sensor plugged into the RAMPS 1.4 shield on top of the Arduino Mega. And this is plugged into the rail, which is designated for the sensors. These sensors come with this cable that's a 3-stranded cable, and there's 3 wires that pop out the other end, and those 3 wires are just raw leads. So they do not have a plug that plugs nicely into any of these male pins on the board, or maybe you're not even using a RAMPS, maybe you have one of the many other type of boards. And if you don't have that sensor plug that you can plug into, what can you use? Well, the answer is you can buy these jumper cables. I think that's what they're called. They might be called jumper leads, and these are just like hobby electronics things that you can buy on eBay. These are female to female. You can get male to female. Anyway, the female ends here plug nicely onto these leads. So obviously you just cut those, splice the wires onto the wires from this, and you're in business. Okay, so back to the sensor. This is the 10 to 30 volt sensor, and it's plugged in because the light's coming on. You can see that 2mm gap. And I had it working on the printer for a number of prints, probably 10 different prints, and it was perfect. Everything worked. The 2mm gap was enough clearance. The problem is I upgraded to this PEI sheet. And I will talk about the PEI sheet in another video here in the future. But basically this sheet is 1mm thick, which means that my 2mm gap went down to about 1 millimeter. It's not good. So I had to go with the 6 to 36 volt sensor that you saw in the last video. Now I bought that sensor at gearbest.com, and that sensor cost me $15. For comparison, I paid $3 for this. So that means I can get 4 of these sensors for the same price. Now, of course, it is superior, but GearBest is out of stock, so we can't even get them from GearBest. I don't know where you would find them. If you find them, let me know. Those sensors are different in form factor because they have a clear plastic top where the screw holes are, and the LED light faces upwards, faces towards the wiring here instead of towards the camera, towards the front. So quite a bit different. But I needed to get a 6 to 36 volt sensor because I needed that sensing distance. And since GearBest doesn't carry them anymore, I went looking all over eBay and couldn't find any 6 to 36 volt sensors on eBay. So I found these on AliExpress. And these are labeled 6 to 36 volts, but the interesting thing is they are not much more of a sensing distance than the blue one here, than the 10 to 30 volt. You can see it's about 2 millimeters. So let's use this sheet of, this is glass, this is a print bed from one of my printers, and on the back side I've put these strips of the aluminum tape that I was showing in the last video. So yeah, if we put the blue 10 to 30 volt sensor on, we get nothing. Touches the glass, no signal, nothing. But if we put the green ones here, these 6 to 36 volt sensors, we get signal from all of them. So they will work to detect the glass, but just barely. Like they're touching the glass pretty much before they detect. Here's something really interesting though. We can see the seam of the aluminum, of the tape. If I put this in the middle, you get nothing, but if I put it on the seam, it detects it. So that means that you're getting a stronger signal from the seams of the aluminum tape. So this is a bad technique. So anybody advocating for this on the internet, which is obviously it's not my technique, I learned of it from the forums, but this is no good. I think a much better solution would be to use an uninterrupted sheet of aluminum foil, maybe spray some Super 77, like some contact adhesive in a can, and then put aluminum foil down instead of this broken thing, because the magnetic flux is stronger at the there at the seams. So no good. So you can see what I've done there. I've just sliced it off in the middle one. And it's really interesting because when I sliced off the plastic, some of this black epoxy, which they bury all of the electronics inside of, but some of that epoxy chipped away and revealed the coil. So there's the copper coil on the electromagnet. And so what's going on there is the electromagnet, and I suspect, but don't quote me on this, I suspect that the electromagnet is flipping polarity, north-south, 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 very rapidly. And that change in polarity is a changing magnetic field. So in order to induce a magnetic field in aluminum, that's induction, right? You need a changing magnetic field. So you can either run a magnet down so you can move it through the aluminum, or you can switch it, flip it, north-south, north-south. And once you do that, the aluminum will emit some magnetic flux. So we have the electromagnet, and right there in the middle, I suspect, is a Hall effect sensor. And that Hall effect sensor, of course, is an analog sensor. But it's been calibrated to know how much magnetism comes off of the electromagnet, how much magnetic flux comes off of the electromagnet. And anything more than the normal amount of flux from the electromagnet triggers the light to turn on. this is a normally open switch, so when the light comes on, it closes the switch and sends that signal all the way up the line to the board. So that's a digital signal. It's either on or it's off. That's what digital means. Of course, the Hall effect sensor itself is analog, but with the electromagnet and the whole shebang, this unit, it is a digital Hall effect based sensor. Pretty nifty stuff. So given what we just learned about why we don't want to use the aluminum foil tape, what I did is I got one of these the glass print surfaces, and I used this Super 77 multi-purpose adhesive, put a light dusting on the glass, and then used some kitchen tinfoil, literally just straight out of the kitchen. And I carefully applied it, first up the middle, and then I squeegeed out the air bubbles with a credit card. And after I'd done that, I put it on the bed here, heated the bed up to 100 degrees, and a bunch of air bubbles formed. So I popped it off. While it was still hot, I used the credit card to squeegee off the bubbles again, and then put it back on the bed again. A few more air bubbles formed, did it a third time, squeegeed out all that bubbles, and third time's the charm, no more air bubbles. We now have a perfectly adhered piece of aluminum foil stuck to the backside of this glass. And as you can see, it works. The sensor detects the aluminum foil quite nicely. Even this 10 to 30 volt sensor is sensing the aluminum foil, if you can check that out. Come on, there you go. So, pretty cool. But what we don't know is what's the distance and if it's a consistent reading on those sensors, if they consistently read the same height. Now, I got a lot of comments in that last video that the consistency might be off on these sensors because they are rated at a higher voltage. They're rated at 10 to 30 volts or 6 to 36 volts, and we're running them off a 5 volt power. So in order to test that, I needed a way to measure the height off the bed. Now, the way that I usually measure distances is with a pair of calipers like this, or I'm sorry, a caliper. And there's really no way to sort of measure the distance reliably with just a hand caliper like this. What I really needed was a digital height gauge. So I have here a really nice caliper. This is a Mitutoyo, made in Japan, comes with a certificate guaranteeing accuracy, all that. And what I did is I designed and printed up these plastic pieces that turn it into that digital height gauge. So you can see it sits on the surface and it raises and lowers there and you get a reading. So what I'm going to do is I'm going to tape this to the table surface right down at the base there, and then it will not move relative to the 3D printer. And what you can do is lower that down, zero it out, and then lift it and lower it back down and get a reading, usually around 2.3, 2.28. There we go. 2.31. Yeah, so you get that reading there pretty consistently as I've been playing with it. So I'm seeing just sort of impromptu tests that it's pretty repeatable, but what we want to know is if it does that when the temperature changes. So hopefully a changing temperature does not change the repeatability in the sensor. Now in order to test that, I'm going to turn the bed off, and it's currently at 100 degrees, and as the temperature drops from 100 degrees down to about 50 degrees, I will just repeatedly take measurements. Now I'm going to use the paper and pencil here to sort of keep track of those numbers, but I'm also going to double check the temperature value here with this infrared thermometer. Now what you get is about, this says 91 and that says 99, so about a 9 to 10 degree temperature difference between the infrared thermometer and the thermistor. So that's interesting. So yeah, I'm going to keep track of all three of those things, and that's the test here. Hopefully we will see a nice, reliable, consistent reading coming off of that 10 to 30 volt sensor, even though it's running on 5 volt power. And it's going to be pretty boring, so I'm probably going to time lapse this. So this is the glass print surface from the 3D printer, and you can see the aluminum foil backing. Now there are a lot of glue bubbles in this application, and that's my fault. I didn't clean the spray tip on the spray bottle before I did the application, so you could probably do a better job applying than I did. But even in like this, it still works, so that's what counts. Now I used this bed for all of the tests. So all of the numbers that we're about to see were done on this bed right here. So here are all of my data points. And I did 5 runs of temperature increasing and decreasing. Now, so 3 of those runs were with the temperature dropping, and 2 of the runs were with the temperature increasing. And I noticed no difference between those. So that means that there's no effect, at least not any that I could observe, with the electricity running through the bed heater. Doesn't seem to have any effect on the reading from the sensor. But surprisingly, temperature has a really large effect on the reading from the sensor. So here is all the data points, and I've graphed them. And you can see a line of best fit going through those data points. Now, if you look here at this lower end, what you see is a nice clustering around the line of best fit. Whereas up here at the top, you notice all of the data points they spread out more around that line of best fit. So what this means is you're going to get more accuracy, more repeatability of the sensor down at the lower temperatures. As the temperature increases, you're going to get more variability. The sensor is going to be less accurate. And not only that, you saw that slope of that line. Well, we're looking at the difference between 50 degrees and 75 degrees Celsius. So in a 25 degree temperature jump there, we get a 0.2 millimeter increase in the distance reading of the sensor. Well, 0.2 millimeters is the width of 2 pieces of paper, and that's a layer height. That's an entire layer height. So that's an unacceptable jump there. So what this means is you need to always do your calibration of your printer, and also the mesh bed leveling algorithm must always be run at the lowest possible temperature. Always do it at the same temperature. That's a low temperature. So maybe room temperature. If you have a consistent 25 degree room, you can always do it at room temperature. That would be best. If you can't do that, maybe the temperature changes a lot in your room, then you can preheat it to ABS temperatures, which are lower. That's in the 50 degree range, and you can always do the test around 50 degrees. So that would be the best thing to do. The room temperature for the calibration, and the room temperature for the auto mesh bed leveling algorithm. So yeah. There's one other question though, and that's aside from the fact of does the value that the sensor gives you change for temperature, that is just does the value of the sensor vary? Is there any, how is the repeatability on the sensors? So to answer that question, I did 50 trials, so just 50 measurements from both the 6 to 36 volt and the 10 to 30 volt sensors, and well, these are the numbers. And I got an average of 2.64 millimeters from the green 6 to 36 volt sensor here. And that has a variance of 0.2 millimeters, which means 1/5 of a piece of paper. So plus or minus 1/5 of this page. It's tiny. And on the blue sensor, I got an average of 2.42 with that same 1/5 of a piece of paper variance. A tiny, minuscule amount. These are absolutely reliable and repeatable for measurements as long as the temperature is consistent. So there you have it. The numbers speak for themselves. So I did one other test. I basically did the exact same thing on my ANET A8 or Troncy machine, and that has an all aluminum print bed. And so the same temperature changes, dropping and increasing and doing the same measurements, and I found a much more substantial relationship between temperature. So in other words, when the temperature increases a little bit, you get an even larger change in the reading of this. So this is extra important if you have a solid aluminum print bed. Okay, so I hope this helps, and hopefully I don't have to do another video on these sensors unless I get my hands on a bunch of the barrel type threaded sensors or something like that. But yeah, I prefer to move on and do more interesting things. So yeah, like I said in the beginning, please go to my Patreon page and send me a couple of bucks. It helps me buy some printers and helps me keep in this hobby and keep the good information coming to you guys. Also, Patreon members are going to have a lot of input as far as the videos that I'm going to make in the future. So if you have something you want to see or you want me to design a part for your specific printer and you're a Patreon donator, well, I'm probably going to do it for you. Okay, so thanks for watching. See you next time.